As I mentioned near the end of our last lesson on scaling waveforms, we need to take a step back and talk about probing. You generally use what's called a probe to get a representation of signals from your circuits into the oscilloscope. You can think of an oscilloscope probe as a stethoscope, which gets a representation of a beating heart into the doctor's or medical technician's ears. Hi, I'm Johnny Hancock, Product Manager for Keysight Technologies Infinivision Oscilloscopes. Let's pick up where we left off in lesson number 2. This is called a resistive divider passive probe. This is the kind of probe that comes with these oscilloscopes, and it's the kind of probe that you'll probably be using most often in your labs. In fact, it may be the only kind of probe. How do you probe? Well, first of all, there's a tip. If you're working with, say, some kind of PC board, you can just touch the tip to the point you want to probe and measure the signals. You can also put on this retractable hook tip connector. And now I don't know if you can see it, but you can hook onto pins and test points and probe very easily. Now, this is the ground wire. It must be connected to ground. You can't connect it mid-circuit. It's the ideal model of this wire is just a 0 ohm wire, but it also has inductance in it. So if you're measuring very high frequencies, the inductance of this wire can make a big difference, and you need to use other adapters to make a shorter connection. Now, if you have any FM radio stations on campus, this thing's also a reception antenna. It can pick up FM signals around 100 megahertz. So you might see that. I've discovered it on some of the experiments I've done. Now, we call it a passive probe because it doesn't have any active components in it like amplifiers. Now, in a later lesson during this video series, we're going to be looking at some active probes that do have amplifiers in them and they require power. These probes have no active components in them, but they do have passive components. Now, what we mean by passive components are things like resistors and capacitors. You probably see on your screen now a high-frequency model of a 10-to-1 passive probe. And we'll explain what 10-to-1 is in just a minute. A high-frequency model of the probe when it is connected to the oscilloscope. Now, inside the oscilloscope is a 1 megohm termination resistor plus 10 to 20 picofarads of parasitic capacitance. And inside the probe, there's a 9 megohm resistor and a couple of capacitors. Some of them are parasitic. Now, what I mean by parasitic is it's not something we designed in. It's just a fact of nature that you have these parasitic capacitances. Now, what we mean by resistive divider is that the signal that goes into the tip gets divided down when it's terminated into the scope. So this particular probe is switchable. It has a 1-to-1 setting and it has a 10-to-1 setting. You should see on your screen now a low frequency model of the passive probe when it's in the 10-to-1 mode. And so now all it is a series 9 megohm resistor in the probe terminated into 1 megohm. And so there you can just use Ohm's law and figure out that what gets to the scope is only 1/10 of what's at the probe tip. So why would we want to divide the signal down by a factor of 10? There are 3 reasons. Number 1, you could measure larger voltages with a 10-to-1 probe. Number 2, and this is probably most important, a 10-to-1 probe has much higher bandwidth than a 1-to-1 probe. And number 3, you have higher input impedance. And what that means is less loading. Now, we can't go into a discussion of that now, but I'll reference a application note I wrote at the end of this video that you can download and learn a little bit more about probe loading. Now, before you start using this probe, first of all, set it either in the 1-to-1 or 10-to-1. And we're going to use 10-to-1 because that's the recommended setting and the one that you should use most of the time. And in fact, your scopes may be fixed 10-to-1 probes. So the first is set it in the 10-to-1 setting. The next step is the probe needs to be calibrated, what we call probe compensation. It's very easy to do. You have to have the right tool though. So let's do it. First, connect the probe to the scope. So I'm connecting it to channel 1. Next, there's a pin on the front panel of your scope. This one says probe comp. That means probe compensation. On your scope, it may say probe cal for probe calibration. So we connect the probe to that pin, and then we connect, there's a ground pin right next to it, connect up ground. Then we need to tell the scope what the probe attenuation factor is. We have the probe set to 10-to-1, so we go into channel 1, select probe, and you can see currently it says 1.00 or 1-to-1. We simply need to change it to 10-to-1, and now all vertical volts per division settings as well as all vertical measurements will be multiplied by 10 to reflect what the amplitude of the signal is at the probe tip as opposed to what's at the input of the scope, which is 1/10 of that. Now, higher performance scopes most of them will automatically detect it's a 10-to-1 probe. Entry-level scopes like this, you need to manually enter it. Next, set up the scope just like we showed in the previous session. I'm going to set the vertical, reposition, set the trigger level about the middle of the waveform, and get a couple cycles on screen. Now what's coming out this pin is a 1 kilohertz square wave. What we're seeing on the scope doesn't look very square. There's a big overshoot on it. This probe is currently overcompensated. If you remember from that high frequency model of the probe, there's a variable capacitor inside the probe, and there's an adjustment near the base of the probe, and your probe should come with an adjustment tool. This looks like some sort of hex drive. You just insert it in there. There's more overcompensation. There's undercompensation. And now it looks like a true square wave. Now this probe is calibrated. I should do the same thing for channel 2. If I've got a 4-channel scope and I'm using all 4 channels, I need to do it for every probe and every channel. You are now ready to use your probe to test your circuits. But let me give you a few additional tips about probing. Always connect the ground lead of the probe to ground in your circuits, as I mentioned earlier. You can't use a passive probe to measure the voltage drop across components in your circuit unless one end of the component is connected to ground. If you attempt to do so, you'll connect a mid-circuit point in your circuit to earth ground, and you might short something out or maybe even blow something up, because this ground clip leads right back to earth ground through the oscilloscope. All measurements using a passive probe should be relative to ground. There are specialty probes that we'll talk about during lesson number 7 that can be used to measure voltage drops across mid-circuit components. You can also use waveform math to compute the voltage drop across a mid-circuit component. We'll talk about waveform math in lesson number 8. Lastly, you may be wondering when to use the 1-to-1 setting on this probe, which turns the low frequency model of this probe into a 0-ohm wire. But it's actually a transmission line, which you may not have learned much about in your studies so far. So it's not a perfect wire. Remember, a 1-to-1 passive probe has lower bandwidth and lower input impedance than a 10-to-1 passive probe. But if you're probing very low-level signals in the millivolts range A 1-to-1 probe has more sensitivity than a 10-to-1 probe, which means that it can measure smaller signals. But for most of your experiments in college, the 10-to-1 setting will probably be the better selection, since you will be probably working with signals in the hundreds of millivolts range or higher. If you want to learn more about 10-to-1 passive probes, there's a probe loading experiment document that I authored that you can download at the URL listed on your screen. In addition to a simple experiment that you can create from 2 resistors to help you better understand probe loading, this document provides a deep dive into the high-frequency model of 10-to-1 passive probes to help you better understand what probe compensation is all about. In our next lesson, Lesson 4, we are going to be talking about oscilloscope triggering, which is a very important topic if you want to master the oscilloscope. And doesn't every engineer? See you again in Lesson 4. Go, Karlsruhe Institute of Technology. If you know what their mascot is, put it in the comments section. I couldn't find it.